Goldgate Engineering Institute. I want to draw your attention to something I've noticed for people who analyze reinforced concrete buildings consistently. I've noticed a consistent error in the design of reinforced concrete buildings, and I need to draw your attention to these errors which I have noticed. Okay, so someone sent a simple two-story structure to help revalidate his structural analysis, and in the course of revalidating and checking the analysis model, I noticed a few errors which I need to share with the group. Now, if you look at this two-story structure, this is the first floor, that is the second floor, and then this is the first floor slab. So let's take a look at the first floor structural layouts, and then we observe the concern that I have with the structural loading philosophy for the first floor beams. So part of the load transfer mechanisms for reinforced concrete structural frames is that the loads are typically transferred from the slab to the beams, and then the beams transfer its loads to the columns, and then the columns eventually transfer its loads to the foundation. So this load ideology and this load transfer pattern must be understood by the structural engineer in the course of developing his loading philosophy. But it's something that needs to be understood. The way the loads will be transferred from slabs to the beams, it's a function of the configuration of the slab. So typically, as known by structural engineers, slabs are either defined as either being a two-way spanning slab or a one-way spanning slab. So the definition of a two-way or a one-way spanning slab is carefully contained or defined explicitly in the Eurocode 211. So it talks about the aspect ratio for the slab. Once the aspect ratio is less than 2, that slab is assumed to span in two directions. Okay, so the deformation of the slab is in two directions. So that's when the slab is categorized as a two-way spanning slab. And then when the aspect ratio is greater than 2, then the slab is sensibly supported along one of its edges. You need to understand that terminology. This is a requirement of the Eurocode. The slab is sensibly supported along one of its edges. Then that slab is defined as a two-way. It's defined as a one-way spanning slab. Okay, so clause 5.31 defines the slab, or defines the slab geometry as either being a one-way or a two-way spanning slab, but that's not essentially. So clause 5.31 subsection 5 gives the explicit definition of what a two-way or a one-way spanning slab is, but that's not the crux of this basic conversation. Now, typically, the way the loads are transferred from the slab to the beams for a two-way spanning slab is different from the way the loads will be transferred from the slab to the beams for a one-way spanning slab. You need to pay very close attention. Now, for a two-way spanning slab, the load will be transferred to the beam based on the yield line failure mechanism of that slab. Now, if you look at this two-way spanning slab that this chap has modeled, now this slab is continuous on this edge. So if I take out this slab, right, if I take out this slab is continuous on this edge, it is continuous on that edge, it is continuous on this other edge, and it is discontinuous on this edge. Now, the way the loads on this slab will transfer to the boundary beams will be a function of the failure plastic yield lines that will form on this slab as it is failing. Now, the construction of yield lines is not what I'm going to lecture in this session, this very basic section. So the way yield lines are constructed is captured in Reinforced Concrete Designer's Manual. So it gives you the rules of formation of yield lines. So typically, for those who are conversant with plastic analysis of structures, you know that yield line forms, at the boundary edges of support. So the yield line forms along supports. Okay, that's one of the rules. Yield line forms. So when a slab is filling, the formation of yield line forms at the location of plastic hinges. So for those who have done plastic analysis, method of analyzing structures plastically. You have the direct statistical approach, and then you have the virtual work methods, where the virtual work theory, where you have the external work done by the external load, or equal to the internal work done by the plastic hinges. So that's not the conversation. So yield line forms at the location of the support point, and then it forms at the intersection between the support. So this is how yield lines are formed when the slab is about to fail. Okay, yield line forms at the intersection between lines of support. Now, the Reinforced Concrete Designer's Manual has gone further to explicitly define or derive the theories associated with the formation of yield lines, and then provides the various yield line formations. So if you look at clause 13.4.2, it gives requirements for how yield lines are formed. They are usually typically formed at the location of lines of support. They are formed, usually yield lines must be straight. Yield lines usually change direction at the intersection between yield lines, which is true. So if you look at this yield line and that yield line, once they intersect, the direction of the yield line changes. Okay, so this is how yield lines are formed. So it's based on the formation of the yield lines that the loads are transferred to the beams. Okay, so based on the formation of the yield lines, the loads are then transferred to the beams. Now, this is very important that people understand how the loads are transferred. I've reviewed different structural analysis model, and you see structural engineers loading beams arbitrarily. Okay, for some who use ridiculous softwares, which I may not mention. Some of these beams are either overloaded or underloaded. It is more dangerous when some of the beams are underloaded because of the lack of understanding of this critical loading philosophy or failure philosophy of reinforced concrete slabs. But this is not again where my attention is being driven towards. Now, so I talked about formation of yield lines. So these are the rules of developing yield lines. Yield lines will change direction at the intersection of two or more yield lines. Okay, yield lines separating two slab elements usually must pass through the intersection of the axis of rotation. Okay, so you also have reinforcements intercepted by yield lines. So these are rules of creating your theoretical yield lines, but that's not where I'm driving at. Now let's look at carefully where my concern is. Now, the code has carefully provided the various yield line patterns. Okay. Right, so the designer's manual has provided the various yield line patterns that would occur on two-way spanning slabs, which will provide information on the loadings that will be transferred to the boundary beams. It gives all the theoretical expressions for the various loads that will be transferred to boundary beams, okay, based on the fixity or the support conditions of the slab panels at the edges. So for all kind of support conditions, for all possible arrangements of support restraints for slab panels, it has given what the yield lines will look like and then the loadings that the beams will be seeing. Now, let's now go straight to the crux of why this conversation commenced. Now, if you look at this structure, the first floor slab, what this fellow has done in the loading of the first floor slab, okay, in the loading of the first floor beams rather. So typically STAAD intelligently derives the loads and transfers them to the boundary beams in line with the failure yield line theory of the corresponding slab. So once you specify or define the location of the slab panel in space, irrespective of this the slab's geometry, without modeling the slab, STAAD automatically transfer the loads from the slab to the beam. So I mentioned earlier on that the loads that the beams will be seeing is a function of the yield line formation on the slab. So as the slab fails, the loads will be transferred to the beam. So the equations for determining those loads that the beams will be seeing is carefully captured in the designer's manual in table 2.52. Now, with all the parameters and expressions defined clearly or succinctly in the table, in the descriptive part of the table below. Now, the concern is, now the fellow has loaded the beams, the boundary beams correctly, but now let's look at this section of the building. This is a very basic building. Let's look at the section of the building. Now you observe that the individual has not loaded the beam. So now this part of the building, the slab panels on this part of the building is a combination of two-way and one-way slab. Now this is a one-way slab panel. This is a one-way slab panel, but this is a two-way slab panel. Now, why is it a two-way slab panel? Let's look at this very carefully. Now, the aspect ratio of, so if you look at this, now for this slab, this is a one-way slab panel. It's a one-way slab panel because the aspect ratio of the longer to the shorter side is greater than 2. Okay, so that's 3.72. So it's 3.72. Therefore, if you analyze this slab manually, and you take a section there, so this is the slab you are to analyze. Okay, once you estimate the loading on the slab, the reaction at the supports, this is what you're going to get as the boundary condition. Okay. So when you estimate the loading on the slab, the total load on the slab is going to the beam. So for this fellow to model to idealize the loading transfer from this slab to this beam is in order. It's in order here, but it is wrong in this slab panel because this slab panel is not a one-way slab. Why is that so? Now, for that slab panel, the ratio of the longer to the shorter side is 1.84. So this slab panel is a two-way slab. Now, because this slab panel is a two-way slab panel, the loading on the beam is not going to be the same as the loading on the beams for this other slab panel. It has to follow the yield line theory to derive the loads on the beam. So because we have specified or talked about the yield line, so this is how the yield lines will form for this slab. This is the yield line formation for this slab. Therefore, this beam will receive a proportion of the load from the slab. This other beam will also receive. So if you look at what the fellow has done, he has loaded this beam alone and has failed to load. He has loaded this beam erroneously, assuming that this is a cantilever, a one-way spanning cantilever slab. So he has loaded this beam wrongly and has failed to load this beam. Okay, so this slab panel, this is the boundary condition of this slab panel. So it is continuous here, it is continuous here, it is continuous here, okay, and then it is not supported here, so you don't have any form of support. So you have yield lines forming this way, okay, and change direction. So you have the loading coming there, you have a load coming there. and then you have a load coming there. How do you get the intensity of the load you're going to apply to these beams? You go back to the designer's manual. So let's look at the condition that applies to what? Okay, fine. So this is the condition that applies to what he is supposed to do. So this is the beam. You have this beam and you have that beam. So this beam and this beam will take different load intensities, which he had not specified in his analytic model. So his analysis will be wrong. The dead load transferred to the beams that he has omitted would invalidate his design results. It will invalidate the reactions at the support which he had used to size his foundations. It will invalidate the deflection criteria and so on, because the loadings were not applied correctly. Now, so look at the loads that is supposed to be transferred to the beam. How is he supposed to idealize the loads? Now, if he goes to this key, you will see the loadings that go to the beams. So you have R4, R1, and R3. So let me use R4 as an example. So the loading to this beam is R4. This is the expression for R4, where K is the aspect ratio, W is the load intensity. If it is the dead load he's trying to transfer to the beam, so W is the dead load. Okay? Right? And then LX is the shorter span. So you have to evaluate this expression and then get R4. So when you get R4, okay, you then get the triangular loading associated with R4. When you do that, you then go to start, define the load. So if you look at what he has done, he has applied a distributed load, uniform distributed load, which is wrong. The loading on this beam is a uniformly I'm referring to this beam. So he has defined a uniform distributed load, which is wrong. The loading on this beam is a uniformly varying distributed load. So you're supposed to go and change the loading, okay, to a uniformly varying distributed load and then apply it on the beam. In the same vein, you're supposed to calculate the loading on this beam. So if I isolate this beam, this is this beam, okay. So the loading on this beam here is like this. That's this beam, which he failed to have calculated correctly. So you're supposed to calculate the loading. The load on this beam is provided as well too as R. Okay, R whatever. So the load is specified. So you calculate the load and then you apply it correctly. So this distance is provided also. So if you go to the designer's manual, the designer's manual also provided the overage over which the load applies. So if you look at this distance, if you go to the key, it provides the distance. Okay, so this is phi LX, and then you now get what the distance is. So where this phi parameter is given as K over 2. So half of the aspect ratio will give you that. Then the difference between that will give you this. So you apply this load and then apply this load, and then you apply the load correctly on the slab panel. So this is just to draw our attention to these consistent failures that I have noticed in the review of several reinforced concrete design. Many buildings are not designed correctly. The load patterns are not idealized accurately, and this has resulted to poor engineering design and poor results that engineers have used in progressing their structural design. It could have its long-term impact, okay, in the durability and the reliability of the engineering design results. Thank you very much.